Hello students. So now that we know a little bit about exponential functions, the next lesson we're going to talk about is exponential growth and decay. Growth and decay are two specific type of exponential functions that we often find in the real world in dealing with finances, sometimes population, or growth of plants or animals. Lots of times in chemistry or biology, you might see cell structures and all that kind of stuff dealing with growth and decay. So we're going to talk about what it looks like and how we would solve a growth and decay problem and how we would set it up first before we solved it. So first of all, we want to remind ourselves that the function for exponential is y equals a b to the x power. Okay, that's important to realize. Okay, because in growth and decay, a and b and x are very specific things. A is the initial value. That could be the initial value of money that you're depositing into an account, or it could be the initial population if you're doing a population growth or decay study. Okay? B is the rate. Okay? The rate will be given as a percent, but you have to change it to a decimal. And that's decimal. So B is always the rate. 36%, 123%, 2%, whatever. Okay? Either way, you've got to change that rate to a percent. And then X, for the most part, when we deal with exponential functions in real world and trying to use them, X is time. Okay? And that could be in days, hours, minutes, weeks, depends on what you're talking about. So, but the X is going to be time. Okay? So, I am going to make kind of a T-chart. Not very much of one, just about that far down. And we're going to do growth on this side and decay on this side. Alright? Growth is identified as y equals a, which is the initial amount, times a quantity of 1 plus r to the x or the t power. Okay? I'm going to put t for time because that's typically what it is. Now typically when you see growth, you're going to see 1 and r already added together. You won't have them separated. So we'll look at an example in a minute. So decay would be y equals a, again, which is the initial amount, times the quantity of 1 minus r, because it's decay, it's going down, raised to the t power. Okay? So let's say, for example, I'm going to do an example. We're going to do an investment fund. Okay? We start with $8,000 at a rate of 2.5%, and I want to know how much I earned after 3 years. So I would plug this in. Y equals A is the initial amount, 8,000, times the quantity of 1 plus R. Well, R is 2.5%. I have to change that to a decimal, so that would be 0.025, so it would be 1.025 raised to the third power. And then I just plug that into my calculator, and that would give me the growth, or the amount of money I would have after 3 years. Let's talk about a decay. Let's say it's a half-life of a cell. Okay, so you probably talked about half-lives in science. Well, we're going to say that there are originally 80,000 cells, and they decrease at 50% every 3 hours. And so then I need to figure out, sorry, not every 3 hours, but at 3 hours, how many cells would I have left? So we do y equals the initial amount, 80,000, times 1 minus 50%, change 50% to a decimal, 0.5. 1 minus 0.5 is just 0.5, raised to 3 hours. And then if I did that calculation, it would give me how many cells are left after 3 hours. Okay, so let's look at something a little bit more specific, and I'm going to use a different color for this. What do you notice in this exponential function about b? Okay, b for growth is greater than 1. But let's look over here at decay. What do you notice about b for decay? B is less than 1, but it's greater than 0. So in decay, b is going to be between 0 and 1, which is essentially a fraction or a decimal, which makes sense because if it's a fraction of something, that's going to be a decrease. And here, with growth, b is always going to be greater than 1 because it's increasing, so it's got to be greater than 1, which is that original amount or initial amount. Okay? Those are the big things that you need to know about the differences between growth and decay. The formulas are the same except for growth is plus and decay is minus. So now let's look at some examples that you might see on an assignment or that you have to work out. Okay? So let's look at number 1. The table contains some points on a graph of an exponential function. Write the exponential function the table represents. So you'll remember, in order to write an exponential function, we need to know a and b. Okay? Now, to find a, remember a, we said this is from yesterday, but also it's the initial amount or what we would consider the y-intercept. So in this case, a equals 0.0625. I know that because x is 0 for a y-intercept, so the y is 0.0625. Now for b, I've got to figure out what my common factor is. So I'm going to look at my y values, and I'm not going to start with 0.0625. That's crazy. Let's start with 1 and 4. How do I get from 1 to 4? They told me it's exponential, so that means I have to multiply something. So 1 times 4 is 4. Now let's go backwards. Is 0.25 times 4 1? Sure is. So I'm going to assume that 0.0625 times 4 is, that's supposed to be times, not a decimal, 0.25. So my common factor is 4. So then to write my equation, it would be y equals a, which is 0.0625, times 4 to the x power. And that would be the way I would write the equation. A and B, plug it in. Now let's look at the second one. The starting annual salary for an office worker at a company is $29,000. The company awards an annual increase of 6.2%. Write an exponential function to model the annual salary increase each year. So we are going to do A is our initial amount, which is $29,000. Okay? B is our growth, or the rate, 6.2%. It's an increase, so I'm going to do 1 plus 6.2%, but I got to change 6.2% to a decimal first. So that'd be 0.062, so B is going to be 1.062. 1 plus the rate is a decimal. And so I have A and B, and now I can write my equation. Y equals 29,000 times 1.062 raised to the x or t, it doesn't matter. I'm not going to put a 1 there because 1 would just be figuring out what the rate would be for, the increase would be for 1 year. But I want to know what it might be for any year, so like in 5 years, how much would I be making at this company? That's why we just put the t. Okay? Now number 3. Number 3 says the U.S. Census has calculated that the city of Radiator Springs is decreasing in population by 11% each year. If the population of Radiator Springs is 8,732 in 2018, estimate the population in 2025. Well, first of all, we've got to write our equation before we can solve anything. So let's figure out what A equals, what B equals, and then we'll write the equation, and then we can solve it. So first of all, I got to know what is my initial amount. Initial amount is 8732, because that's the population right now in 2018. Now what is my rate? The rate is 11%. Is this going up or going down? Yep, you're right, it's decreasing because it says decreasing, so I've got to take that 1 minus 0.11, and that would be 0.89. Again, if you look back here in the equation, 1 minus whatever the rate is as a decimal, so 11% is 0.11, 1 minus 0.11 is 0.89. So now I'm going to write my equation. Y equals 8732 times 0.89 to the t, or the x, it doesn't matter. Now, but this asks me to calculate what it is. So now I've got to calculate it. So I'm going to rewrite it with t included. Y equals 8732 times 0.89 to the what power? If it's 2018 now, in 2025, that would be 7 years. So then I'll calculate it to 7. And so now I'm going to use my calculator. Let's turn that puppy on. Let's go home and let's do a new document. And we'll do no. And I need to calculate. So I'm going to do 8732 parentheses 0.89 close parentheses raised to the 7th power. And here. Now, you're going to think, well, what do I round to? Well, we're talking about population, which we're talking about people. So we can't have a fraction of a person, so we have to round to the nearest whole number. So that would be 3862. So in about 7 years, Radiator Springs will have about 3862 people. Is that exact? No, because we don't know that it's exactly going to increase or decrease by 11%, but that's just an estimate that people would use. Okay? So again, when we're doing exponential growth and decay problems, look for your initial amount, look for your rate, and either add it or subtract it to 1. And that 1 stands for the 100% of the total. Okay, so we would always subtract. Or add, depending on if it's growth or decay. And then either write the equation or solve the equation, whatever the question asks you. Now for Math Workshop, just bring this paper completed, and we will just make sure you understand what you're doing.